We do have some questions from our panel members. And as you said, we'll go to the Q&A right now. Karen, you have a question for Chase?
Yeah, Chase, I did. Thank you for this presentation. This is great, great information. But one thing that jumps out to me is the combining of conventional observations with your GNSS observations, particularly in a least squares adjustment. Um, how do you go about weighting that? What kind of scale do you use? I mean, they're apples and oranges. So how do you
Yeah,
turn them all into one fruit?
Karen, thank you so much. That is a great question. And the issue that we're talking about here is that oftentimes when you're doing those baseline reductions, you're trying to get your solution from real-time GNSS, whether it be real-time networks or single base. Oftentimes the modeled or the estimated error of that solution is pretty optimistic, right? So it could think that you're getting sub-millimeter accuracies, right? And so if we were to use that by itself as the weight in our least squares adjustment, it's going to appear to be much more accurate than our conventional measurement types, right? And so what we implemented when we did this is we leveraged the program software, and I'm not advocating for any particular software. Mostly squares adjustment software packages will have some type of feature like this. Is I scaled those estimated standard errors from the GNSS. I scaled them such that I could satisfy some of my statistical tests to evaluate if my stochastic model is properly weighting these observations. So I ended up actually having to scale those. I do find with real-time network observations, it does produce more realistic estimates of those errors than single base RTK. Because we are getting better models of the troposphere and the ionosphere, I generally find I only have to scale my real-time network estimated errors by 2 to 3. We performed a lot of least squares adjustments in that study, a couple hundred of them, and we always found that it was around 2 to 3 is what we had to scale them by. Whereas with our single base RTK, it's oftentimes around 10 to 15 that I have to scale them by, so they're much more optimistic. Does that answer your question, Karen?
It does, except what happens when you combine, say, total station or leveling data in? The total station data is not going to be as internally consistent as GNSS. So how do you manage that?
I think it all comes down to making sure you're weighting your observations appropriately. So I tend to find that my total station data it's very precise relative to itself, right?
Really? Okay.
And so assuming I'm modeling my stochastic model correct. So if I'm modeling the errors of my total station, whether that be the distance error or the angle consistency, so that standard error, as long as I'm modeling that appropriate, I find that things actually tend to work very, very well. Where you can get in trouble is if you start being overly optimistic or pessimistic with your standard error models. So what I would say to help you with this process is get more familiar with the precision that your instrument is able to provide. There's some ways you can do this empirically. One of the things you can do is you can set up your total station, set up some targets that you typically use, and just make a bunch of redundant measurements, right? Go out there and measure 100 times, the same angle, same distances. Compute the standard deviation of that, and that's a pretty good representation of that standard error of that instrument. And you can use that in your stochastic model to help weight that adjustment. It's going to give you pretty accurate results. You can do similar things with GNSS. I could go out and I could make a bunch of redundant measurements to the same point and try to estimate what that standard error is, assuming you do have a good reference data set for that point. So those are good ways to do it empirically. You can dive into the theory of it a little bit more and really try to do some formal error propagation based off of manufacturer recommendations and things like that. But I would say what gets people in trouble the most is they're not able to model their instruments errors accurately.
Yeah, that's good information because I'm thinking in terms of pointing error, which is not something you have with GNSS. So
Sure.
good answer. Thank you.
Yeah, thank you.
Okay, Muge, you have a couple questions, I see, for Chase.
Yes. Hello, I am Miguel Bayrak. Chase, thanks for your presentation. I have two questions about the slide that covers how many observations you need. My first question is, what are your suggestions for repeating observations? Do you think 3 repeat observations in the Oregon real-time GNSS network would be sufficient to achieve high vertical accuracy? How should these repeats be separated in time?
Oh, that's a great question. Let me go ahead and I'm going to pull that slide up again. And let me share my screen. So this is a slide we're talking about where we went through and we did the study and we tried to represent what our overall accuracy, again, these are reported at a 95% confidence level, what that accuracy would be based off of redundant observations. And so looking at this, your question was, well, would 3 redundant observations be good enough? Would that give me the accuracy I need? And
Yes.
I don't think you're going to love my answer because my answer is it depends. What accuracy do you need to achieve, right? Where are you working in? Are you combining it with other observations? What does your sky visibility look like? Is there some multipath issues, right? So my answer is that it's going to vary a little bit, right? Whether it's 3 or 4. And it's going to be kind of project specific. But in general, what we're finding is you're not seeing a lot of improvements beyond 4 observations. And so you're kind of going to get pretty close to the best results you're going to get when you get 4 or more observations. So that would be my general recommendation. If you're really trying to get the best accuracies you can, obviously, the more redundant observations you get, the better. Again, didn't think you'd like that answer because it's not a very straightforward answer, right? Your other question of does time between those repeat observations matter? That is a great question because we actually evaluated this, and I didn't show the slides on it, but if you read the paper, this study, which again, we'll post a link to that study in the description of this video. If you read that study, we actually evaluated time between repeat observations. How does that affect our results? And we evaluated repeat observations at 1 hour, 2 hour, and 3 hour intervals. And what we found is our repeat observations are still correlated if your observation durations or repeat observation times are less than 3 hours. And the reason why they're still correlated is our satellite constellations have not had enough time to move. And so statistically, we're still kind of getting the same solution if you do it an hour back to back. And so when I say repeat observations, what I don't want people to do is say, oh, well, I'll observe 5 minutes, stop, store. I'll observe 5 minutes, stop, store. I don't want you to do that back to back. We need to add some time between that. So we give those satellites enough time to shift over and we get a statistically independent solution, right? That's really what we're looking for. And then the other thing is when I'm saying repeat observations, I want them to be independent observations. I don't want it to be correlated with my last solution because what if that last solution had an issue with it? So in those repeat observations, what I would like to do is get a new initialization. And I want to make sure that I am resetting up over the point. I want everything to be completely independent of those last observations, right? So by doing the whole 3 hours in between, you're going to help ensure that you're getting that. If you actually go through and you read that NGS NOS 92 report, they are also recommending the same thing, around 3 to 4 hours in between repeat observations. Yeah.
Can I follow up real quick on that?
Yes, please do.
I thought 92 recommended on a different day, but I know the original 58 and 59 recommended not only 3 hours, but on a different day, so you had different atmospheric conditions.
Mhm.
Does 92 do that? What did your study do? Was it on the same day?
We did ours on the same day. Yes. So ours was spanned over. It was actually spanned over a 2-day period. And I think part of the different day, obviously, that's better. But when you start thinking of practicality, doing it different days is a little bit more of a challenge. But I do want to talk about different days, because if you are going to observe on different days, what we don't want to do is observe 9 a.m. on day 1 and observe 9 a.m. on day 2, because we're going to have the same constellation, pretty close to the same constellation at those times. And so you want to try and, again, the goal is different constellations. So observe at times we're going to get a varying constellation, right?
Yeah, that's how I thought 58 was. It was on one day and it was 27, at least 27 hours later
Yeah.
than the other day. So you had the 3 hours on a different day.
Yes. Yeah.
Very good. Sorry to jump in, Nuge. You had another question.
Yeah, for my next question, the vertical accuracy, specifically the ellipsoidal heights shown in your presentation, looks good. I wonder, after the beta release of the new GEOID from NGS, GEOID 2022, have you observed any improvements in the orthometric heights in comparison with leveling and water level gauges?
Ooh, that is a great question. I have not explored GEOID 2022, at least not as rigorous as we've done in this study. So I can't answer that question. But my understanding is that the estimated uncertainties in the geoid separation values in GEOID 2022 and the geoid slope are better. So I would assume that we're getting better estimates of orthometric heights. We can dive into that a little bit more and how NAPGD 22 is generally going to agree better with orthometric heights, because we're defining it as the orthometric height is equal to the ellipsoid height of that new datum plus our geoid separation. So it's defined that way. So in general, you're going to see some better agreements there. Whereas NAVD 88 orthometric heights, which we're using geoid 18 in this study to get to, that's using a hybrid geoid model, right? And so it's more of an approximation where the orthometric height from GNSS is approximately going to be equal to our ellipsoid height plus that hybrid geoid model. And so I think just based off of how they've defined these systems, I do think that you would get better agreement using GEOID 2022 and our new vertical datum, just because they've defined it that way. But yeah, that would take a lot more time to dive into. Good question,
Thanks.
though.
Yeah, very good answer too. By the way, I'm glad that you said that geoid 18 is a hybrid geoid. And so it's not really a geoid, it's more of a transformation surface, but geoid 2022 will be a real geoid model. Okay, great answer. I guess, Brian, do you have a question?
I think my original question was answered earlier, so I'll change it up and ask you if these amazing results are available in a peer-reviewed journal article or stored somewhere else that we can access them.
Good question. So we are actually still working on publishing the peer-reviewed article. So that is in progress. But our report that we submitted to ODOT, so this study that I presented all these results on was a study funded by the Oregon Department of Transportation. And so that very lengthy and detailed technical report has been published. And so you can access that full thing. But the peer reviewed article is still in progress. When those are available, the ones that are available we'll have Mugate include in the video description. And then when we get that other article published, we'll also include that there for people to read.
Great, thank you.
All right, I have a few questions, and some of them are pretty straightforward. That you mentioned in your RTN position how to know if it's accurate. and you mentioned one way is to check a published mark. So how do you know if the published coordinate of the station is good, if it's up to date, or even accurate enough to check your work? So you check on it, and or so let's say you don't check on it. What do you do when you don't check on it because maybe it moved, maybe it's not your system, maybe the mark is it? What do you do next?
That's true. Yeah. So, I mean, that gets into how do you determine a position relative to the NSRs that you are confident in? And there's a couple ways you can do that. You could do a couple long static observations and get a solution from Opus. Cool. That's one approach. You could do a full GNSS network kind of analysis using Opus projects. Again, incorporating lots of data. I generally don't recommend just pulling the NGS passive benchmark, like published elevation, out of the NGS database, just because, again, maybe that mark hasn't been surveyed since, I don't know, 2002, right? And so, again, stability of that mark can be a concern. There are certain benchmarks, passive benchmarks, that are very stable, right? They're tied into bedrock, and so maybe we're a little bit more confident in those elevations. But I would say it depends, right? From my experience, what I found is a lot of different surveying outfits, they'll have some control points that they're very confident in, that they have observed multiple times. Typically, it's out front of their office, and it's a point that they are feeling confident in. And so I would say use those. In some situations, though, maybe you're working on a project, and you were given some control that you have to tie into. So someone did a control survey, they gave you the coordinates, and that control network is what's being used for that construction project. Maybe that control network isn't actually tied to the NSRS. So you're not going to get those from the RTN, even if it is aligned to the NSRS, you're not going to get the coordinates that you need. And so in those situations, what you might do is perform a localization, right? Localization, I think, is a term, maybe it's that Trimble uses, but essentially what you're going to be doing is a local site calibration where you observe a handful of points using that real-time network, and you say, hey, I observed them. I got these coordinates from the RTN. This is what my coordinates should be. This is the control that was given to me by somebody else. This is what I need to tie into. And then it goes through and it basically determines what those transformation parameters are between those two. And then it gives you those parameters and it applies them to your entire GNSS project. That's one thing to do. I generally don't like site calibrations because it creates this like one-off coordinate system that is hard for data transferability, right? Because now when you transfer that data, you need to attach what those transformation parameters are so that people can get into that local coordinate system you've created.
Yeah. Okay. Another thing that you talked about was acceptable range is 2 centimeter horizontally and 4 centimeters vertically. And I know that I worked for NGS when they were doing this. So I know that that's a criteria that's pretty common. I've done a lot of work in subsiding areas, and so 4 centimeter vertically is not stability. It is moving, and we know it is. And also, there's small tilts that could be occurring that so in your recommendations, I guess, when you say that just because you get that, you should be looking to make sure that it isn't in a subsiding area, or there isn't something that happened to the antenna, other than just saying, well, it moved, but you don't know why. Is some investigation on it?
Yeah, absolutely. And I think that question, William will cover that a little bit more. And how do we manage and monitor these RTN stations? Because that's really what that question is kind of stemming towards is,
Yeah.
how as a user am I confident in the position that I'm getting from this reference network? And so that's what a lot of our research is focused on is how do we monitor these? And then if we do find that the position is maybe drifting over time, how often do we update the published coordinate to that reference mark, right? How often do we get new NSRS positions for it? And so that's the question that we're trying to answer with that funded research, where we've been trying to develop this RTN alignment and monitoring service utility.
Yeah.
Yeah.
Okay. So, and my one last question. So, North Carolina, where I live, has like 99 stations in their RTN system. So, in their space, and you're within 25 kilometers, wherever you are, you're within 25 kilometers of one of their cores. So, do you think that they would get better results that you would get from your Oregon network? And I mean, do you think they should do their own study to determine that, yeah, maybe 3 will always work, maybe 4, or maybe whatever, even less in some areas? What do you think?
Yeah, I think it's a great idea for any RTN to perform. It doesn't have to be at the scale of the study that we did here, but I think it's a good idea for any of them to go through and evaluate the accuracies they're getting from that network. I think there's some reluctancy for users to adopt leveraging a real-time network because they're like, I don't know what accuracies I'm getting from this. And so I think if there's these different RTN managements or management groups or operators, if they want people to adopt it more, perform a study, show them, hey, these are the results we're getting, and this is how we got those results. That's going to help increase confidence. Yeah, back and talking as to whether I think North Carolina is going to get the same results as what we get in the ORGN. Again, it's gonna vary. What is the overall health of those reference stations, right? Are they pretty stable stations, right? Do we get good NSRS positions of those stations? Do we know where those positions are, not just relative to the NSRS, but relative to each other? That's going to be a factor in things. And then overall base station kind of distribution or distance between those reference stations. That's also going to affect our results. And so I would have to look more specifically at North Carolina. But in general, some of those principles I talked about, if you have stations that are much closer to each other, I would expect you to get better results. And I believe, talking about the positions of them, I believe most of the reference stations in North Carolina's real-time network are NGS cores. But just because those cores are positioned relative to the NSRS by NGS, they were positioned relative for a much larger scale NSRS position, right? And so that accuracy of 2 to 4 centimeters was probably good enough for them. Whereas for a real-time network, I generally find we actually want to improve our relative accuracy a little bit better to get more consistent results across the network. And so what you might find is a real-time network operator might actually adopt slightly different coordinates for those reference stations than what NGS has published. And the reason why is they might run a full network adjustment between just those stations to help improve the relative accuracy. So they'll do baseline processing from reference station to reference station to help get a better relative accuracy amongst those reference stations. And then they'll constrain that to the NGS published values. But essentially, we let them shift just ever so slightly. So you might see slight discrepancies between an NGS published coordinate and a RTN adopted position.
Yeah, that opens up a
Can of
worms when you start saying, well, it's not going to be an NGS published coordinate. But that's now, so saying that, unless someone else has another question, we could move on to what William's going to talk about, which really fits into what you were just talking about of your RTN, really aligning it and making sure it's aligned to the National Spatial Reference System.